So what I'm hoping you get out of this section is that you're able to make a sketch of what a polynomial function looks like, and without having to graph it, because you're going to have to be able to do that in calculus. So let's get you ready for that. So, like for number 9, this is from section 3. What page is it? Of course, if they change the addition, this is from section 3.3 in the David Lippmann, Melanie Rasmussen textbook. What we got to do is decide what this looks like. Well, I see, and I'm going to kind of do it all with these questions, even though they don't all ask that. So for question number 9, they're saying find the long run behavior. Well, that's good. It's not hard, and we want you to do that. But we'll also see that there's 3 zeros, so we know it crosses the t-axis in this case in 3 different places. So it crosses it at 5. 1, 2, 3, 4, 4, 5. I'll put a point there, and it also crosses at 3. I'll put a point there, and it crosses at 2. Oh, this is going to be miserable. This is why they want us to graph it. And then I also know the y-intercept. Let's get at the y-intercept. H of 0 is, what is that? That's going to be 3 times negative 5 cubed times negative 3. Remember, I substituted in 0 for t. That's squared, or that's cubed. Oh, no, this is the 5th. No, they're all cubed. All right. Times negative 2. So what am I going to get? A negative 125, a negative 27. There's a negative 2. I'm seeing 3 negatives, so I know the answer is negative. And it's going to be a huge number, isn't it? And so it's going to be 3 times that huge negative number. So that graph, that is way down here. I'm just going to say that's it. Okay, I'm just trying to make a sketch of it anyways. I also see what degree is this polynomial. And this is kind of where we want to go with this, the long run behavior. So way out at positive infinity, way down at negative infinity, or even big numbers. Positive 100, negative 100 would do it for us. The 5, the 3, and the 2 here. Let me get a pointer going. Where is it? Here. See, the 5, the 3, and the 2 really don't matter from way out at negative 100 or positive 100 or negative 1,000, positive 1,000. So see, those don't matter. So all we really need to worry about is the t. So 3 times t cubed, cubed, times t cubed again, times t. Well, that's going to be 3 times, t cubed times t cubed is t to the 6th times t to the 1st is t to the 7th. So I know that acts like a 7th degree equation or a 3rd degree equation. So that tells me the ending behavior of this function is going to look something like this. Let's see, can I move this whole thing up? More or less I can here. We'll move this all up. And they're telling me to make a sketch of it. So I know if it's an odd degree equation, it's going to look like this out at infinity and down like this at negative infinity. As x goes out to positive infinity, y goes out to positive infinity. As x goes out to negative infinity, y goes out to negative infinity. So that's the ending behavior. So that tells me it's going to look something like this. I know it's got to cross through this point, and it's going to head down to negative infinity. And probably some kind of curve going on. Then I've also know these things in multiplicity. So I see that at 5, or actually let's start backward. Let's start smallest. At 2, that's just multiplicity 1. So that's just going to pass through. But somehow it's got to turn around and go through 3. So I'm going to come up. It's going to pass through. Somehow it's going to turn around. And then it's kind of got to wiggle through that x equals 3 one, right? Because it's 3rd degree. Then it's got to turn around. Then it's got to come down here and turn around. And it's got to wiggle through. It's got to wiggle through that. And then it's got to head up here to positive infinity, right? Because we knew that's where it was ending. It's got to act like, let's see, can I hide this? Let's see if it'll let me draw a rectangle to square through this. Oh, good, look at that. See, when I'm talking about ending behavior, I don't really care what's happening in the middle. I want to know what's happening out at negative infinity, positive infinity. When I'm when I'm talking about, let's see, how do I delete? When I'm talking about, can I move that? Okay, oh, I can delete right here. When I'm talking about at x equals z, on the short run behavior, I'm talking about where's the y-intercept, whoops, where's the y-intercept, where are the zeros, what is it acting like at those zeros? Granted, this is a pretty crappy graph. I mean, that's not even a function the way I drew it, but because it fails the vertical line test. But you get the idea, right? So that's what I'm hoping you can do. Now, number 11 is kind of interesting because I see a negative in front, so that tells me it's reflected around the x-axis, and I also see, or t-axis in this case, I also see there's another swap there, so that's a y axis reflection. Maybe because it's squared, it won't matter, but that's something we got to think about. Okay, so let's see. I see. Let's figure out what the ending behavior is, since that's what it's asking us to do. So I see a -2 times a t times another t times a -t squared, right? Remember, we don't care about the constants out at infinity. We kind of keep the 2 because that's a, that's like a reflection. That's causing a reflection. So I'm seeing, let's see, I'm seeing a -2 times a t times a t times a positive t squared. So what is that? -2t to the 4th power. So that tells me the ending behavior is going to look like this. Head down this way, and it's also going to head down this way because it's an even degree power. Acts like x squared, except the -2 flips the graph, right? So what's the ending behavior? Well, I know, let's see, can I move everything up? I know that as x, let's answer the question, as x approaches -infinity, y also approaches -infinity because it's at even degree. And the same deal when we go out to positive infinity, y also goes out to -infinity. I almost said positive infinity. And then it's got some stuff happening in the middle. Let's see what we can do. Okay, so I see, so we're talking about number 11 still. Whoops, get a pen going, Dan. I see across the x-axis or t-axis is 0 because of that. I see it crosses the t-axis at 1. Here, I'm going to stretch this out. And then it all crosses the t-axis at, let's see, where would that be? Where it is 3 minus t equals 0. Well, that's t equals 3, right? So 1, 2, 3. Well, 3. So it crosses here, here, and 0, 1, and 3. We'll pretend 3 is right there. And then I know the y-intercept's also 0 because if t equals 0, the whole thing's 0. So then, and I see there's a multiplicity 2 at the 3, right? Now, I really think because this is being squared, you don't have to worry about that reflection. We'll see here. Let's see. So I know it has to act like this. Out at -infinity, it goes down here. At positive infinity, it heads down here. I see it's got to pass through. Here, let me go to a red ink. It's got to pass through 0. It's got to turn around, pass through 1. And then it's going to bounce at 3. So it's going to come, because we know where it's got to head. We know it's got to head there, so it can't pass through that x-axis and come back down. So it's got to look something like this. Okay? So that's what it is. Now, granted, sloppy graph, we don't know where these turning points are. We really don't care where they are, at least at this point. You know, you'll in calculus, you'll learn how to find those. But that's how that graphs. So I'm hoping this helps. Notice I haven't grabbed a calculator at all and haven't even had to think too hard to do this. So it's where I want you to go. Okay? Hopefully it helps.